Section 4.1 Vector Spaces and Subspaces. A vector space is a non-empty set, we'll call it V, of objects, which are vectors, on which are defined two operations, addition and multiplication by scalars or real numbers, and they're subject to the 10 axioms that we're going to look at. The axioms must hold for all vectors u, v, and w in our set V, and then for all scalars c and d. So the first axiom is that the sum of our two vectors is also in the set, that when I add, that the order does not matter. The same thing, basically the associative rule, that I can group them differently and we still are in our set and we have the same answer, or they're equal to one another. There is a vector called the zero vector in that set such that when I add it to a vector in V, I get that vector back. So u plus 0 is equal to u again. For each vector u and v, there is a vector negative u such that when I add the two together, I will produce the zero vector. When I multiply by a scalar, that is also in my set. When I multiply the sum of two vectors, I can then distribute that scalar to both and add that, and that axiom holds, they're equal to one another. The same is true if I was to add the scalars and multiply that by a vector. I could split that up, multiply the vector by each scalar and then add, and that's also equal. I can change the grouping with the multiplication by scalars. And then lastly, I can multiply by a 1 and still get, and that's a scalar 1, and still produce the same vector. So those 10 axioms have to hold in order for us to have a vector space. And in this example, they've given us a vector space which we'll call M sub 2 by 2, and this is the set of 2 by 2 square matrices A, B, C, and D such that the entries are real numbers inside. And we want to determine if this is a vector space. So this is the set of matrices. We know that since our numbers inside are all real, that they can also be all zero. So we know then that there is a zero vector. So we've satisfied that axiom, which was number 4, that we have a zero vector where all the entries are zeros. Now, by the properties of matrices, which we've studied in previous chapters, we do know that all of the other axioms hold for this set. Since we're just dealing with a matrix, we know that that's true, that all of those are true for a matrix. So then this set is a vector space, the set containing 2 by 2 square matrices with real entries. So we know that this is true because all 10 of those axioms held. And we didn't have to do a whole lot of work proving all 10 of the axioms because we've been studying matrices, so we know that those were true just by definition of being a matrix, and we know those properties hold for matrices. When we're dealing with other spaces, we probably will need to actually look at some of those and make sure that they hold. So let's look at another example. In this example, we're going to let n greater than or equal to 0 be an integer, and let p sub n be the set of all polynomials of a degree at most n greater than or equal to 0. So they have this form here, where the a sub 0 through a sub n are real numbers, and t is a real variable. And so we want to determine, is this set p sub n a vector space? We're going to verify 3 of the 10 axioms in this example. So first, let's define another vector in this set. We're going to say q of t is equal to this vector, where our real number coefficients are b sub 0, and t is still our variable. So this is another vector in the set. And first we're going to look at axiom 1 and prove it and show that it is true. Remember that axiom 1 said that the sum of two vectors that are in the set to begin with is in the set P sub n. So we'll check to see that that's true. I'm adding P plus Q, and P plus Q is defined in the following way. P plus Q of T, we know since these are polynomials, we know with our rules of algebra that this is simply P of T plus Q of T. So this is going to be equal to P of T with our A's as our coefficients plus Q of T with B's as coefficients. And what we can do then is we can group like terms. So what we end up with then is A sub 0 plus B sub 0 as our first term, plus then A sub 1 plus B sub 1 times T, plus all the way up to A sub n plus B sub n times T to the n. And this is also a polynomial of degree at most n. So then we've shown that P plus Q is in P. So we've shown axiom 1. Now we're going to look at axiom 4. And remember that axiom 4 stated that the 0 vector is in our set V. So first I'm going to define the 0 vector to be 0 plus 0t plus all the way up to 0t to the n. And this is the 0 vector in our set P sub n. So I want to show that when I add that to a vector that's also in the set that's not the 0 vector or a non-zero vector, that I will end up still having the same vector. So P plus the 0 vector of T will be then P of T plus the 0 vector. So that is going to be A sub 0 plus 0 plus A sub 1 plus 0 of T plus all the way up to A sub n plus 0 T to the n. And that is simply then equal to A sub 0 plus A sub 1t all the way up to A sub n T to the n, which was P. So we've then shown that this axiom holds. And the last one that I want to look at is axiom 6. And we want to show that when we multiply by a scalar, that is in V as well. So we want to show that if I multiply by a scalar, that C times P is in P sub n as well. C times P of T is simply equal to C times then P of T, which is equal to C times A sub 0 plus C times A sub 1 T plus all the way up to C times A sub n T to the n. And since our A's were real numbers and we're multiplying by a real scalar, we still have real numbers. So then this is in P sub n as well. And you can check that the other 7 hold as well. They do. So what we're saying then is that P sub n is a vector space. And there's a reason that we looked at only these 3. And we're going to look at that next. We're going to talk about subspaces. Vector spaces may be formed from subsets of other vector spaces, and these are called subspaces. A subspace of a vector space V is a subset H of our original space V that has these following 3 properties. The 0 vector of the original space is in the subset. For each U and V in H, the sum is also in H. And in this case, we would say that H is closed under vector addition. And then the third property is for each vector in H and each scalar C, multiplying by that scalar is also in H. And so in this case, we would say that H is closed under scalar multiplication. And so if these 3 properties are true, then our subset is a subspace. And if the subset satisfies these three properties, then H itself is a vector space. The set consisting of only the zero vector in a vector space V is a subspace of V called the zero subspace, and it's written in this manner. We have the set notation and just the zero vector inside. The vector space R2 is not a subspace of R3 because R2 is not even a subset of R3. Remember, elements vectors in R2 have 2 entries and elements in R3 have 3 entries. So we're not dealing with a subspace since it's not even a subset. Elements in R2 are not also in R3 and vice versa. However, we are going to look at something where we have something in R3 that resembles R2. And in this example, we have H being equal to the set of vectors A, 0, B, where the second entry is always 0 and the first and third entry, A and B, are real numbers. So we want to show that H is a subspace of R3. To show it's a subspace, we need to show that those 3 properties hold. Remember, the first property is that the zero vector is in H. And that's the zero vector of R3, of our original space. So we're going to let A equal 0 and B equal 0, and then we will get the zero vector, which is the zero vector here in R3. And that is also in H. So we've shown that the zero vector of R3 is an element of H. Next, we want to show that H is closed under vector addition. So we have 2 vectors in H. We're going to add those together. So A, B, C, and D are real, and the second entry is 0. And when we add those together, we'll have A plus C, 0, and B plus D. And so what we see is that when I add 2 vectors, I will always, as long as they're 2 vectors that were in our set, I will always produce a vector whose second entry is 0 and the other entries are real numbers. So I'm adding 2 real numbers to accomplish that. So then the sum is also in H. And we see that H is then closed under vector addition. And the third axiom, we want to see that it's closed under scalar multiplication, meaning multiplying by a real scalar. So when we multiply any vector in H by a real scalar, we produce another vector that is in H as well, because we're multiplying and we'll have real numbers in the first and third, and we will still have 0 for the second entry. So anytime I multiply 0 by a non-zero number, I still get 0. So then H is a subspace of R3. So I was saying at the beginning of that example that we were kind of going to look at how these resemble R2, these vectors that are a subspace of R3. And the vectors in H look and act like the points A, B in R2. Because we have 0 for the second entry, they still are just looking like the Cartesian plane. So right here, this point is A, 0, B, but it does look and act like the points A, B in R2. In this next example, we want to determine if our set H, where we have x and then x plus 1, and x is a real number, if that is a subspace of R2. So what we have then are the ordered pairs x and then x plus 1. So really what we have is basically that y equals x plus 1. So here what we've got then is the graph of x plus 1, this line here. And if you look, the point 0, 0 is down here, and so it is not on the line. So property A is not true because H does not contain the 0 vector. If we let x equal 0, then x plus 1 would be 1. So we'd have the point 0, 1, which is obviously not 0, 0. So the 0 vector is not there. So then H is not a subspace of R2. And to show that it's not, we can disprove any of the 3 properties. We've kind of used the easiest one, first one, the 0 vector. If the 0 vector is not there, it's not a subspace. However, sometimes the 0 vector is there and it's still not a subspace. So I'm going to show you how we could have used one of the others in this case to disprove. So I'm going to let the vector u be 0, 1, and then I will let the vector v be 1, 2. And these are vectors in H because the second entry is 1 more than the first, and that's what this said, x and then x plus 1. So then I want to show that it's not closed under vector addition. So if I was to take u plus v, then I'm adding my two vectors together. So I have 0 plus 1, which is 1, and 1 plus 2, which is 3. And this is not a vector in H. So then property B fails as well. And we'll kind of look at the graph here. The graph of u would be right here, 0, 1, and that is a point on our line. The vector v is right here. So this is u and v, but we see then that u plus v would be the point 1, 3, which is up here, and that is not on the line. So that's another way to see it visually. In this example, given v1 and v2 in a vector space v, we're going to let H be equal to the span of those two vectors, and we want to show that H is a subspace of v. And remember the definition of span, that's the set of all linear combinations of those two vectors. So for property A, I want to show that the 0 vector is in H. So basically I want to show that I can write the 0 vector as a linear combination of v1 and v2, and we can because we'll simply write it as 0 times v1 plus 0 times v2. So then we've shown that the 0 vector is in H. To show the second one, we want to show that it is closed under vector addition. So I'm going to define two vectors. I'm going to let u be s1 v1 plus s2 v2, and w be t1 v1 plus t2 v2. So these are two vectors that are a linear combination of v1 and v2. And I want to show then that u plus w will produce another vector that is in H, or another vector that is a linear combination of v1 and v2. So I'm adding these two vectors together, and I can reorder them, and I have s1 v1 plus t1 v1, and then plus s2 v2 plus t2 v2. And now I can look at them, grouping them this way, and basically factor out v1. So I have s1 plus t1 times v1 plus then s2 plus t2 times v2. And remember, s and t, s1 and s2 and t1 and t2 are simply scalars. So when I pull them out, they're still scalars, and so then this is a linear combination of v1 and v2. So this is in H as well. So we've now shown that it's closed under vector addition, and now we want to show that it's closed under scalar multiplication. So if C is any scalar, then when I multiply C times the vector u that I had in part B, I will have C times s1 v1 plus s2 v2, and I know that I can basically distribute C. So I have C times s1 v1 plus C times s2 v2, and I can group my scalars together, and this is also in H. So then we've shown that it's closed under scalar multiplication. And so H, being the span of two vectors that were in V, then H is a subspace of V. So this leads us to a shortcut for determining subspaces. Theorem 1 says that if I have vectors v1 through vp that are in my vector space V, then the span of those vectors is a subspace of V. So now here's my shortcut. The first way to show that H is a subspace of a vector space, we can apply theorem 1. If it's a linear combination of the vectors, then it's a subspace. Or, to show that a set is not a subspace, provide a specific example showing at least one of our axioms A, B, or C from our definition of a subspace is violated. So in this example, is V, which is equal to A plus 2B and then 2A minus 3B, where A and B are real, is that a subspace of R2? Why or why not? So first thing I'm going to do is I'm going to write this in column form. So I have A plus 2B and then 2A minus 3B. Now I can split that up to being A and 2A plus then 2B and negative 3B. And now I can factor out an A out of the first vector, and I have 1, 2, plus B out of the second vector, and I have 2, negative 3. And if we define these vectors here as V1 and V2, and these vectors V1 and V2 are vectors in R2, and A and B are scalars being multiplied by them, so this is a linear combination of those two vectors. And so what we've just shown is that V is equal to the span of the two vectors we just defined, V1 and V2. And so then by theorem 1 from above, we know that V is a subspace of R2. So if we can take a set and show that I can write it as a linear combination of two vectors, then I can apply that theorem 1, and say that that is a subspace. In this example, we want to answer the question, is H, defined here, a subspace of R3? Why or why not? We cannot do what we did in the prior example because there is not a B in each of the terms, so we couldn't factor B out. So we can't write it as a linear combination. And so now we want to try to provide a counter example. And we can basically show that the 0 vector from R3, which is the set of 3 zeros, is not in H. Since if I let A equal B equals 0, or any other combination of values for A and B, we will not produce the 0 vector. So property A fails. So therefore H is not a subspace of R3. Now you try. I want you guys to look at this example, this set H of all matrices of this form, and determine if it's a subspace of M sub 2 by 2, which we defined earlier in this section, which is basically 2 by 2 matrices with real numbers in them. And we are assuming that A and B are real. So what you need to do is you need to either show that we can write this set H as a linear combination of two vectors that are in M sub 2 by 2, and so apply theorem 1, or show that one of the three axioms from the definition of a subspace doesn't hold. Work on this and we'll talk about it in class.